All right, grade 9s, I'm here to help you get through topic 7 in our electricity unit. For the first few pages of in your textbook, it will help you complete your notes package. Okay, so let's get started here. So the first thing we're going to talk about, boys and girls, is how electricity actually gets to your house from the generating station where it's produced. So for electricity to get to you, of course, first it's going to be generated at a power station. Then the next thing is that it needs to go to what's called a step-up transformer. So this is a transformer that takes a small voltage and steps it up to a much higher voltage because we want the power lines that leave the generating station. We don't want a whole lot of power lines, so we want each power line to take a large voltage of electrons in that wire. Then they're going to be traveling to a substation, and from the substation they're going to be passed on to a distribution station. The distribution station then uses a step-down transformer to take the voltage of the electricity down because it's eventually going to be delivered to your house. So you don't need super high voltage. We want the high voltage to be able to travel over long distances, but by the time it gets to your house, we want to take that voltage and make it a voltage that the appliances and the circuits in your home are designed to withstand. Now, of course, the electricity, it's going to go through an electricity meter because we have to pay for our electricity, so that has to be recorded. And then it's going to go to your main electrical panel, which then can distribute that electricity through all the circuits in your house. Now, guys, in order to help your circuits in your house not to get overloaded, to get fried, or for your loads on those circuits to get too hot or break down, we have fuses and we have circuit breakers. Mainly in your house, it's going to be circuit breakers, but depending on whether you maybe have a cabin or an older electrical circuits, it could be fuses as well. Together, they simply protect the conductors and the loads on those circuits from being damaged. So the next couple of slides are going to kind of help us understand how they work. So starting with a fuse, so a fuse is like an extra resistor or load that you put on the circuit. It has a very thin wire that's going to be sensitive to the amount of current or voltage that you have in that circuit. If the current gets too high, well, then the resistor or this thin wire gets too hot and it will melt. And when it melts, it breaks the circuit. So instead of allowing your conducting wires to melt or your load or resistor to catch on fire, the fuse blows, and then of course the electricity stops in that circuit, and all you need to do is replace that fuse and then solve your problem so that the fuses don't keep being blown, and then your circuit is protected. Or we have what's called a circuit breaker, which is in your electrical panel. You have all these switches. Well, each one of those switches is a circuit breaker.
Could Juan come to the office, please? Juan, thank you.
There we go. And it works using a bimetallic strip, so two metals bonded together. Now, just like the thin wire in a fuse, if too much current starts to run through the bimetallic strip, it gets hot. But instead of melting, it starts to bend because the metal expands as it heats. And when you have two different metals, they expand at two different rates. So that causes the metals to curl. The curling action breaks the circuit. And there again, protecting that circuit from too much current. And then the beauty of a circuit breaker is that once it cools, and it can cool quite quickly, you can reset your breaker. And then you don't have to keep replacing fuses. You just take that breaker switch and move it all the way over, and then move it back, and then your circuit's ready to go again. Now, guys, your electrical devices and the electrical wiring in your home are managed by electrical codes. So these are put in place by the government. They're safety standards so that your wiring is safe and your device is safe to use. Many digital devices have very, very small circuits in them. These are called transistors, which were larger in the day, but as technology has progressed, we've been able to make micro transistors, and these are what make up your microprocessors of like your calculators, computers, of course, and many, many, many devices now are run by microprocessors, but they all work the same way. They're still circuits, but they're almost microscopic. They follow what's called a binary code, which is a series of zeros and ones programmed to turn those little tiny circuits either on or off, which allow them to work and make decisions and do whatever they need to do. It's the language of computers. Now let's turn our attention to power. Guys, power, and you've heard of electrical power. What power is, it's a rate of electricity usage. And it's in units, that means it's measuring the amount of electrical energy per unit of time. That time is normally seconds, and the unit of energy, if you remember, are units of joules. So to calculate power, because it's a rate, that usually means anything over time. Power is E for energy in joules over time. Our unit for power is the watt, which you've no doubt heard about because when you buy light bulbs, you need a certain wattage. Well, that's telling you how much energy per second that electrical device creates. So power in watts is equal to energy in joules divided by time measured in seconds. So really, what is a watt? 1 watt of power would be 1 joule of energy produced or used every second. Now, a more common way of measuring power, because we quite often know the current, I, in a circuit and the voltage of that circuit, if you multiply I by V, you get power. All right? So for example, let's take a look at a current of 13.6 amps passing through an electrical baseboard heater when it's connected to 110 volts, which is typically the voltage that the circuits in your home are invented for. So what would be the power of this heater? So using our formula, power is equal to IV, 13.6 amps multiplied by 110 volts gives us 1496 watts. So this heater creates 1496 joules of energy, which would be heat for a heater, every second. Now, to give you some perspective, that's quite a bit of power. A typical microwave is usually working on 1,000 watts or 1,100 watts. So this particular heater would be using about 1.5 times the power of a microwave. Now, power is usually labeled on a device. So for example, we know that light bulbs are ranked by watts, so is a microwave, but you may have heard of these things called kilowatts. Well, kilowatts, 1 kilowatt, it's like a kilometer being 1,000 meters. A kilowatt is 1,000 watts. So 1 watt is 1,000th of a kilowatt. Now we have another unit. Guys, you're going to get lots of units in this topic here. Another unit you may have heard of is called a kilowatt hour. All right, so a kilowatt hour, and quite often sometimes we can pay for our electricity by kilowatt hours, or kilowatt hours can be the energy usage that we see on appliances. Sometimes that's called an EnerGuide number. So what is a kilowatt hour? Well, that's simply taking the watts divided by 1,000, because that's what creates a kilowatt, multiplied by the time in hours that you use the device. And it's a way we can often compare the electrical usage of different devices. So, as I mentioned, we have to pay for our electricity. So when we pay for our power, we have to be able to get a reading off of an electric meter. okay? Because it's going to determine the consumption of power. So of course you've got a meter, it's either in your house or on the outside of your house that can be read either directly or sometimes it's read now from a distance electrically. But guys, as a skill, you have to be able to look at these dials and determine the amount of usage. All right, so for example, and this is in kilowatt hours, if your previous if your previous reading is, and notice we get our numbers here, so because it's between the 6 and the 7, be careful, the dials run oppositely. You've got to be careful which way the dials move. So obviously we're greater than 6 because we're between 6 and 7, okay? And then greater than 3, so we need to go 6, 3, and then less than 6, right? So we're between 5 and 6, so the next number is 5, and then of course the last number is going to be 7, okay? And then the new reading, we can even have another dial, so we're going to have 5 numbers this time. Greater than 5, 4, between 2, because we're between 2 and 3, 7, because we're between 7 and 8, and 2, because we're between 2 and 3. So the current reading is 54,272. So to determine the kilowatt hours of usage, just simply subtract. Okay, we're going to take our current reading, subtract the old reading, gives us the amount of kilowatt hours that have been consumed, and you can be charged per kilowatt hour. Okay, so I hope you can. The screen isn't getting washed out too much for you. All right, so guys, in your notes package, you have practice problems to work on. Okay, now let's determine, here's a question. It says, if a fridge requires 800 watts of power to function, how many kilowatt hours of power will it require in a 30-day period? So we can start by finding our kilowatt hours by dividing by 1,000. So 800 divided by 1,000 is 0.8 kilowatt hours. We know that there's 24 hours in a day. We're running this fridge for 30 days, so that's a total of 720 hours. So for kilowatt hours, we simply multiply the kilowatts by the hours, and we get 576 kilowatt hours. So therefore, this fridge is going to use 576 kilowatt hours if it's running for 30 days. If you know that your electricity costs, say, 10 cents per kilowatt hour, then how much is it going to cost to run this fridge for the month? You simply take your dollars, that's a tenth of a dollar, right? 10 cents, $0.1, multiplied by our 576 kilowatt hours. So that would cost us $57.60 for that fridge, assuming that it's running constantly. But of course, we know fridges actually turn themselves off and on depending on how much they're being opened and closed. So again, you've got a little bit of reading that you can do in your textbook. To determine consumption, you've got some problems to do in your notes package. Now, another thing we need to talk about, guys, speaking of paying for electricity, we want to be as efficient as we possibly can, because the more efficient your electrical device is, the less money you're going to have to pay for using it. So to calculate efficiency, we have another formula, no units this time, guys, because efficiency is actually a percentage. And it's a ratio between the useful energy output of that device versus the total energy input. So if we think of a light bulb, for example, its input energy is electrical, but its output energy is light. So if we were to calculate the efficiency, we would really be comparing how much energy did it start with compared to, in terms of electricity, versus how much energy of light did it actually produce. And that'll be a percentage. If all the electricity gets turned into light, that would be 100%. But that will never happen, all right? Because every time we change one form of energy to another form of energy, we always lose some energy as a waste product. So let's look at an example. Let's say we have a 1,000-watt kettle and it takes 4 minutes to boil some water. If it takes 1.96 times 10 to the 5 joules of energy, By the way, down here we can take this. This is scientific notation. The 5 tells us that we need to move the decimal place over 5 places. So don't worry too much about that right now. Just so understand that the electrical energy that the kettle gets is 196,000 joules. All right? All right, so we need to figure out the efficiency. All right, so moving right along, we need the amount of time that the kettle is going to run for. So the kettle is going to take 4 minutes to boil the water. So we know that that's 240 seconds. Using, remember the formula, power is equal to energy over time. If we rearrange the formula, we know that energy is equal to power times time. So we take our 1,000 watt kettle, multiply by the 240 seconds that it's running for, and we get a total energy of 240,000 joules. Well, that's our output energy, right? Okay. So to find our efficiency, we need to take our useful output energy, right, and divide by the total input energy. Okay. All right. Oh, I'm sorry. This was the electrical energy, so my mistake. This electrical energy actually is the input energy that the kettle got. The output energy is what we calculated, or what we saw before on the previous slide. So sorry about that, guys. So the previous slide shows us that this is the actual energy that the kettle made heat. All right? Yeah, see, there's our heat energy, and the heat energy is the useful output energy. So there we go. But the actual electrical energy provided was 240,000 joules. So so our useful output energy, 196,000 joules, divided by the total electrical input energy, 240,000 joules. We multiply that by 100%, because this will always be a decimal, and we get an answer of 81.7%. Okay, so that's a pretty good efficiency of turning electricity into the heat that actually heats the water in the kettle. All right, so again, guys, in your notes package, you can see that there's some more practice problems to work on. Okay, so there you go. So hopefully that helps, and enjoy doing your practice problems.